Hi everyone, we are from Group 1 and today we will present our lab experiment and the topic is minor losses in pipe. Next, I pass to the next presenter.
The summary of this report. Experiment 4 is an experiment about minor losses in pipe to determine the loss coefficient KL associated with HLM. The total energy loss in a pipe system is the sum of the major and minor losses. Minor losses are associated with the value of loss coefficient KL. The value is strongly dependent on the geometry of the component considered as well as the fluid properties, includes the RE. In most practical cases, the value of KL for a component is a function of geometry only. In this experiment, the KL value and HLM in pipes are for different water flow rate, pipe diameter, and pipe bands will be determined. The KL of the tested geometrical was determined by these two descriptions. First by sudden expansion or enlargement and sudden contraction, and second by elbows, pipe bands, and pipe branches. Next, we got the theory. The flow in piping system at different flow rates may be required to pass through a variety of lifting bands or abrupt changes in area. Additional heat losses called as minor head losses (HLM) are encountered, primarily as a result of flow separation by simplifying the Bernoulli equation between 2 points for horizontal Z1 equal to Z2 pipe. The pressure loss and the total head loss HLT could be determined as follows. The below are the equation 1 to equation 5. Next, for the P1 minus P2 is pressure drop between 2 points, and the density represented by the density, and G represent the gravity constant, and V1 minus V2 represent the changes of velocity of flowing medium from point 1 to point 2, and HLT represent the total head loss, HL equal to the major head loss, F equal to coefficient of pipe frictions, and L is the length of the pipe, D is the internal diameter of pipe, V for HL is the speed of flowing medium for the tested pipe, and HLM is the minor head loss. V for HLM is the speed of flowing medium in the vicinity where the minor loss occurs, and KL equal to the loss of coefficient associated with HLM, and H1 minus H2 is the differential height in manometer between point 1 and point 2. Next, the value of HKL. If the value of KL is strongly dependent on the geometry of the component considered as well as the fluid properties, includes the RE, and the mathematical function of them can be expressed in the equation 6. As shown in the equation 6. In many practical applications, the RE is large enough so that the flow through the component is dominated by inertial effects, leaving the viscous effects as secondary importance. In a flow which dominated by inertial effects, it is usually found that pressure drops and head losses correlate directly with the dynamic pressure. Therefore, the friction factor for very large RE in fully developed pipe flow is independent of the RE. The same condition is found to be true for flow-through pipe component fittings. Thus, in most practical cases, the KL for component are a function of geometry only. In this experiment, the KL value and HLM in pipe for different water flow rates, pipe diameter, and pipe bands will be determined. The description related to each of the tested geometrical is as follows. First, the sudden expansion or enlargement and sudden contraction. KL for sudden expansion or enlargement and contractions in circular duct pipes are shown in Figure 2. Note that losses for the sudden expansion or enlargement are based on speed of flowing medium at region 1, whereas for sudden contraction are based on speed of flowing medium at region 2. Next. So this is the Figure 2 showing the loss coefficients for flow through sudden area changes. Next. The value of KL for the fluid flow through a sudden expansion or enlargement and contraction can be obtained by considering the continuity in equation 7 and momentum in equation 8, an energy equation between point 1 and 0.2 for the control volume shown in figure 2. The resulting three governance equations are as follows, and those equations can be rearranged to give the theoretical KL for sudden expansion or enlargement in equation 9, whereas the theoretical KL for sudden contraction can be expressed in equation 10. So the second part is the elbows, pipe bands, and pipe branches. The value of HLM and KL for the flow involving pipe components floating such as elbow, pipe bands, and pipe branches could be determined experimentally using the equation 3 and equation 5. An example of typical value of KL for pipe component floating are shown in figure 3. Next. So this is the figure 3 showing the typical value of KL for pipe component and fittings. Next, I will pass to the next presenter.
Okay, so next we move on to procedures. So first what we need to do is we need to determine the direction of water inflow and outflow for the tested pipe section. And next we need to fully open the inlet valve, which is by turning it to anti-clockwise direction of the tested pipe section, and close the inlet valve by turning it to clockwise direction for the non-tested pipe section. Next, we need to turn on the pump and slowly open the outlet valve, which is by turning it to anti-clockwise direction until maximum, which means fully open, and wait for a while in order to remove any air bubbles for the tested pipe section. Fourth, we need to identify the inlet flowing pressure, which is H1, and the outlet flowing pressure, which is H2, for the tested pipe section, and connect the manometer tubes from those H1 and H2 on the tested pipe section to the tube manometer H1 inlet and H2 outlet, and we need to record the values of H1 and H2 at 2 tube manometer. Next, we need to determine the actual water flow rate, which is Q actual, by recording the time taken to collect 3 liters volume of water at the tank. Next, we need to reduce the opening of the outlet valve and repeat steps 4 and 5 for 5 different values of Q actual. Next, after finished, we need to remove the manometer tubes first to avoid the bubbles in the tube. Ninth, with the pump in running condition, we need to repeat steps 1 to 7 for the other tested pipe section. And last but not least, after finished, remove all the manometer tubes from the system, fully close the inlet valve and outlet valves, and turn off the pump and the main switch. Next, I will pass the result analysis part to the next presenter.
Okay, I will carry on for the data analysis part. We are required to calculate and record a few of our findings in the table stated. For the table, we have pipe section where we categorize the pipes into the ones mentioned earlier. Next is volume of water collected, which is measured in liters, time, which is in second, actual flow rate, which is in liter per second, H1, which is in millimeter, H2, also in millimeter, and last but not least, delta H, which is difference in H, also in millimeters. This is our findings. This is for sudden enlargement. This is for sudden contraction. This is for Y-type pipe. This is for T-type pipe. This is for the 90 degrees angle. This is for the 90 degree bend. And last but not least, this is for the 45-degree angle. For the discussion, it asks us to calculate the minor head loss and loss coefficient for each of the pipe components fittings. Set the temperature of flowing medium to 36 Celsius and determine the coefficient of friction using a formula of Blaze's. And these are our findings. Now I pass on to the next presenter.
I will continue our discussion to discuss the effect of different water flow rates, pipe diameters, and pipe lengths on the value of loss coefficient. The loss coefficient in both laminar and turbulent flow is proportional to the free velocity. Since it obeys this equation, minor head loss equals to kb squared over 2g. The friction loss in flow increases as the free velocity increases. The rough pipe has a much higher friction loss than the smooth pipe in turbulent flow. As a consequence, the pipe's surface influences the friction loss in turbulent flow. Pipe roughness, on the other hand, has no effect on laminar flow. Hence, friction loss in smooth tubing is unaffected by pipe roughness. This is due to the roughness being covered by the flow. Therefore, the pipe's roughness can have an effect on friction loss. The rougher the pipe is, the higher the value of loss coefficient, and thus the greater the friction loss. Furthermore, the free friction factor of a pipe is inversely proportional to its diameter. Since area is inversely proportional to loss coefficient, as the pipe diameter decreases, the cross-sectional area decreases, causing loss coefficient to increase, and friction loss will be greater. Moreover, free flow through a pipe band is a highly complex phenomenon. In the region of the pipe band, the fluid has a higher velocity inside the elbow than on the outside, resulting in a large pressure gradient. An unbalanced force apparent in the fluid as a result of the pressure gradient consisting of secondary flow downstream of the elbow. Therefore, when the angle of the pipe bed increases, the loss coefficient increases as the secondary flow downstream of the fluid flow increases. Let's briefly discuss on factors contributing to errors or inaccuracy in experimental data and the possible recommendations to improve the existing results. Many factors contribute to errors and have an effect on the accuracy which experimental data is recorded. Firstly, trapped air bubbles in the connecting tube that connects the pipe to the manometer can block the flow of water and change the turbulent structure. Furthermore, because of the unstable flow rate, the manometer current height fluctuated throughout the experiment, affecting the accuracy of the data collected from the manometer. It is also difficult to set up a constant water flow rate because of the fluctuating flow rate, particularly when we need a constant volume of water collected at 2 liters and 3 liters. Furthermore, Pare's error occurs when the ice level is not perpendicular to the scale of the manometer when taking the water level reading. To avoid mistakes, many precautions must be taken. We must first ensure that all trapped air bubbles are removed by opening the valve and allowing the water to overflow before we begin the experiment. To minimize the error caused by the fluctuation of the water level in the manometer, several readings should be taken and the average of H1 and H2 should be taken. Let's take approximately 2 liters and 3 liters of water and measure them with a more sensitive instrument such as a measuring cylinder to solve the problem of taking a constant volume of water. Finally, the observer's ice level must be perpendicular to the manometer scale when taking the water level reading to prevent Pare's error. Next, I pass to the next presenter.
Okay, so next, we move on to the last part presentation. So in conclusion, for the minor losses, the pipe had 7 different fittings that have different losses based on the type of fitting. The result analysis and discussion shows that the pressure drop increased as the velocity increased. The highest pressure drop came from a right angle fitting, which is a 90-degree angle, while the lowest pressure drop came from an enlargement fitting. The key values are found in the discussion in part 1 based on the results in these experimental values compared to theoretical values. The highest percent error came from a contraction fitting and the lowest percent error came from the right angle fitting. The differences in the fittings came from the theoretical values not taking everything about the pipe into effect. The experimental K value was found to be directly proportional to the pressure drop, and we can see that this is relates the loss coefficient K to the head loss of the system. So that's all from us. Thank you.